Hello, I'm Ryan Young, and today we're doing Module 26209, Grounding and Bonding. Let's get started. Module 26209, Grounding and Bonding. Successful completion of this module prepares you to do the following: identify and describe grounding requirements and applications, identify and describe the purpose of grounding and bonding, and state the grounding requirements for various systems. Performance tasks. Your instructor will have various performance tasks for you to undertake. Grounding system is an important part of an AC system. Its purpose is to protect life and equipment against the various electrical faults that occur. This module explains grounding and bonding requirements of the National Electrical Code. It also explains how to size the main and system bonding jumpers, as well as the grounding electrode conductor for various AC electrical systems. Grounding requirements. The grounding system is a major part of the electrical system. It's possible for abnormal voltages to appear at certain points in an electrical system on the electrical equipment connected to the system. The grounding system provides a path for misdirected current to protect people and equipment from electrical faults. It gives the overcurrent protection device a low impedance path for fault current, so the overcurrent protection device can actuate quickly. Fast actuation of the overcurrent protection device, either a circuit breaker or a fuse. If you have a high impedance path to ground, it'll take a while for enough current to flow in order to affect that overcurrent protection device. Grounding and bonding is one of the most important sections of the National Electrical Code. You can look at the size of it. It's the largest article in the National Electrical Code, so it's very important. It says a circuit is grounded to limit the voltage on a circuit and improve the overall operation of the electrical system. Grounded is connected directly to ground or to a conductor that extends to ground. So when we say ground, we mean the earth we stand on. When we refer to ground, we're essentially talking about the earth. If a conductor is connected to the earth or to some conductive component that extends to the earth, such as a driven grounding electrode or a metal cold water pipe, the conductor is said to be grounded. Here's a highlight. It says the grounded neutral conductor is permitted to be smaller than the hot ungrounded phase conductors only when the neutral conductor is properly and adequately sized to carry the maximum load imbalance as computed according to NEC section 220.61 and 230.42. So in a lot of cases, the neutral, the grounded conductor, is only going to be carrying the imbalance between the ungrounded conductors. And in a lot of cases, the National Electrical Code will allow us to size the neutral conductor smaller than the ungrounded conductor. It must be pointed out that per section 250.24D1, the grounded conductor must not be smaller than the size referenced in NEC table 250.102C1. So the grounded conductor, the neutral conductor, cannot be smaller than the main bonding jumper. It has to be able to carry all fault current imposed on it. NEC section 230.42 outlines the minimum size and ampacity of service entrance conductors and references NEC Article 220 for minimum rating and size computation requirements. NEC section 220.61 states that the feeder neutral must be the maximum imbalance of the load, which is the maximum net computed load between the neutral and any one ungrounded conductor. So the neutral conductor, that's the conductor that is grounded. It's the conductor connected to the neutral point of the electrical system that is intended to carry current under normal conditions. So the neutral conductor is a current carrying conductor. Neutral conductor in a three-phase or four-wire system, for example, is intentionally grounded and therefore becomes a grounded conductor. The wire used to connect the neutral conductor to the grounding electrode is referred to as the grounding electrode conductor. In Article 100, under the definition of grounding conductor equipment, informational note number 1, it recognizes that the equipment grounding conductor also performs bonding. The difference between grounding and bonding, grounding is taking it to the earth. Bonding is to connect two pieces of metal together to make them electrically at the same potential. If you have two pieces of machinery in the same room and they're metal, you take a wire between them, connect them together, you've just bonded them together. If you take a wire and extend it to the earth, to ground, or to some wire in place of the ground, or that extends eventually to ground, you've grounded that system or that equipment. So here's figure 1 panel board showing grounded and grounding conductors. It's highlighted, meaning this entire drawing is a highlight. So study it. If there's something you have a question about, ask your instructor. Here are the ungrounded conductors. Those are the hot conductors going to the main disconnect, the circuit breaker. This is the grounded conductor, which is the neutral conductor going to the neutral bus bar. It's tied also to the grounding bus bar. They're tied together in the main panel. You'll tie the grounded conductor, which is the neutral, and the grounding conductor, which is the equipment ground, and the grounding electrode conductor that goes to the ground rod outside, or to the cold water, or to a plate or steel or ground ring, a metal pipe, some grounding electrode. That conductor that goes to the grounding electrode is the grounding electrode conductor. So the grounding electrode conductor, the equipment grounding conductors, and the grounded neutral conductors all tie together at the main bonding jumper. And it's in the main panel on the neutral bar, the main bonding jumper. That main bonding jumper can be a screw, it can be a lug, it can be a strap, it can be a wire, but it bonds all of those things together. All right. What's wrong with this picture? Well, it looks like somebody stepped on this or rode, maybe they drove over it. It looks pretty crushed. The grounding prong is gone. You can't use this on a job site. The hot neutral conductor prongs are bent out of shape. So, yeah, this has been subjected to something. Something drove over that. Grounding and bonding. Remember, grounding is taking it to earth. Bonding it is connecting two metal parts together. Systems must be solidly grounded to limit the voltage to ground during normal operation and to prevent excessive voltages due to lightning or line surges. I'm going to highlight that. That's a highlight. I'll read it again. Systems must be solidly grounded to limit the voltage to ground during normal operation and to prevent excessive voltages due to lightning and line surges on that system. They're also grounded to stabilize the voltage to ground during normal operation to make sure that we have 120 volts from A phase to ground to neutral and from B phase to neutral. We don't have a floating neutral. We have to make sure that the grounded conductor, which is the neutral conductor, is solidly grounded to earth. Conductive materials enclosing electrical conductors or equipment or that form part of the equipment are grounded to limit the voltage to ground. It presents the following specific requirements. NEC Article 250 is the primary governing article for the proper application of grounding and bonding. This article covers general requirements for grounding and bonding of electrical installations. It presents the following specific requirements. Systems, circuits, and equipment that are required, permitted, or not permitted to be grounded. Circuit conductors to be grounded or grounded systems, ungrounded systems, excuse me. Location of ground connections. The type and sizes of grounding and bonding conductors and electrodes, the methods of grounding and bonding, conditions under which guards, isolation, or insulation may be substituted for grounding. Have sufficiently low impedance to facilitate the operation of the protective devices in the circuit or ground detection for high impedance grounded systems. Be capable of safely carrying the maximum ground fault likely to be imposed on it and not rely entirely on the earth as an effective ground fault current path. We cannot use the earth as a conductor. It's funny, at the same time, they will tell us that the earth is both a good conductor and not a good conductor. We can't rely on the earth to be a circuit conductor, but it will conduct electricity if your standing on the ground and you touch an ungrounded conductor, you're going to get hurt. So it is both a good conductor and not a good conductor. I know that sounds silly, but it's true. Permanent or reliable and continuous grounding systems are vital to the safety of electrical systems. Intermittent connections and are unpredictable and may result in hazardous situations. Since current does not flow through grounding conductors most of the time, it's extremely important to have good connections that will withstand the test of time. Equipment will keep running, but when it malfunctions, the enclosure can become electrified and hazardous. Under normal circumstances, the equipment grounding conductor is not a current carrying conductor. When there is current flowing on the equipment grounding conductor, it means something went wrong. That conductor is there just as a safety to allow a low impedance path for fault current. When we have fault current, it allows enough current to flow to facilitate the fast actuation of the overcurrent protection device. The grounding electrode conductor, the equipment bonding jumper, and the equipment grounding conductor must be adequately sized to ensure there's sufficient capacity to protect the system. Methods to determine the proper size of these conductors will be presented in this module. Short circuit. A short circuit is when the current takes a shortcut. It's not necessarily flowing outside the path of current flow, but it went around the load. It didn't go through the filament of the light bulb. Maybe the hot and the neutral were touched together, so there's a short circuit or a shortcut. Short circuit and ground faults are commonly misunderstood. Both typically stem from a failure of the insulation resistance. It's important to have a clear understanding of these two conditions. A short circuit, this is a highlight, is a conducting connection between any of the conductors of an electrical system, whether it's from line to line or from line to neutral. That is a short circuit. When you involve the earth or ground, that's a ground fault. So there's ungrounded conductors and the grounded conductor, the neutral between them. If there's ever a fault between an ungrounded and the grounded conductor, that's a short circuit. Or if there's a fault between two ungrounded conductors, that's a short circuit. The failure might occur from one phase conductor to another, or from one phase conductor to a grounded neutral. The maximum value of fault current is dependent on the available capacity the system can deliver to the point of the fault. The maximum value of short circuit current from line to neutral will vary depending on the distance from the source to the fault. The available short circuit current is further limited by the impedance of the arc where one is established, plus the impedance of the conductors to the point of the short circuit. Ground fault. This is where the ground is involved. A ground fault, as defined in Article 100, is an unintentional electrically conducting connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors, metallic enclosures, metallic raceways, metallic equipment, or the earth. So it all has to do with going from ungrounded to earth. That's a ground fault. While not specified in the National Electrical Code, an unintentional electrically conducting connection between the grounded conductor, the neutral, of an electrical circuit and the normally non-current carrying conductors, other metallic objects, or earth would also be considered a ground fault. While the first instance, an ungrounded conductor, may result in a large amount of fault current flowing in a properly installed grounded system, the latter may result in parallel paths being formed between the grounded conductor and the grounding system. These parallel paths would result in an unwanted flow of current on the grounding system. So you can have a fault between the grounded conductor and the equipment grounding conductor, and you get current flow. They call it parallel neutrals. It is still a ground fault, but it may not be as catastrophic, or if you're not on a ground fault circuit interrupter, it won't trip the breaker. It'll continue to operate in that condition. 1.2.0 Types of grounding systems. Two general classifications of protective grounding are system grounding and equipment grounding. System grounding and bonding relates to the service entrance equipment and its related components. That is, one system conductor is grounded to limit voltage due to lightning, line surges, or unintentional contact with higher voltage lines, as well as to stabilize the voltage to ground during normal operation. The equipment grounding conductor is the conductive path used to connect non-current carrying metal parts of equipment, raceways, and other enclosures to the system grounding conductor, the grounding electrode conductor, or both. Equipment grounding conductors are bonded to the system grounding conductor to provide a low impedance path for fault current that will facilitate the operation of overcurrent devices during ground fault conditions. Sometimes they refer to the system grounding as being line side grounding. In other words, it's the grounded conductor, the neutral conductor coming in on the service and going to the main bonding jumper being tied to the grounding electrode conductor and to the equipment grounding conductors. They call that line side grounding. Load side grounding is the equipment grounding conductors going to the equipment to facilitate a low impedance path for fault current. So 25066 in the code book will deal with line side grounding, the grounding electrode conductor, and 25122 will deal with the load side grounding, the equipment grounding conductors for equipment. Grounding single-phase systems. To better understand a complete grounding system, we'll examine a conventional residential beginning at the power company's high voltage line and transformer. Pole-mounted transformer is fed with a two-wire 7200 volt system that's transformed down to a three-wire 120 240 volt single-phase electric service suitable for residential use. Wiring diagram of the transformer connections is shown in figure 5. So here's the pole-mounted transformer. You have one ungrounded conductor at 7200 volts to ground coming into the primary of the transformer. The secondary is tapped to the grounded neutral. This solidly grounded neutral from the 7200 volt source ties into this secondary side. And it also goes to the transformer case, and it's also taken to ground with a ground wire, usually run exposed on the side of the pole and secured at close intervals. It goes to a ground rod. Ground wire runs down to the bottom of the pole and is connected to a ground rod, ground ring, or ground plate. And then it ties into the messenger cable holding the ungrounded conductors and the neutral going to the house. A lot of times the neutral is bare and it's wound around this steel messenger cable. The steel messenger cable can take the stress of being hung in free air, and the other conductors are wrapped around it. So you're not putting that tension on the aluminum wires. Let's see, what does this say here? Note that the voltage between legs A and B is 240 volts. However, by connecting a third neutral wire on the secondary winding of the transformer between the other two, the 240 volts split to provide 120 volts between either leg A or leg B and the neutral conductor. Consequently, 240 volts is available for household appliances such as ranges, hot water heaters, and similar loads that consume more energy. 120 volt legs are available for lights and electrical receptacles and smaller loads. So here's a highlight. It says, referring again to the diagram, conductors A and B are ungrounded conductors. Conductors in an electrical system that are not intentionally grounded, sometimes referred to as the hot conductors, while the neutral conductor is a grounded conductor. That's the highlight. The neutral conductor is intentionally grounded. It's taken to earth. If only 240 volt loads were connected, the neutral or grounded conductor would carry no current. However, since 120 volt loads are present, the neutral will carry the unbalanced load and become a current carrying conductor. So the neutral conductor only carries the imbalance between leg A and B. If you have 20 amps flowing on leg A and 18 amps flowing on leg B, you're only going to have 2 amps flowing on the neutral. It's the imbalance between the two. Here's a highlight. It says, for example, if leg A carries 60 amps and leg B carries 50 amps, the neutral conductor would only carry 10 amps. So that's a highlight. Here's another highlight. It says, this is the point where most systems are grounded at the neutral bus in the main panel board. So we we bond the grounded conductor with the grounding electrode conductor and the equipment grounding conductors all at the main bonding jumper in the main panel at the neutral bus. Warning, it says exercise extreme caution when disconnecting a grounding electrode conductor. Never touch a disconnected grounding electrode conductor at anything grounded, including the grounding electrode, at the same time. Should a fault current occur, your body will become a conductor of the current. The results could be fatal. So when you disconnect the grounded conductor, treat it as a hot conductor. All right. So here's the incoming service. Here's the weatherhead and the service mast coming down to the meter socket. There's a main disconnect on the outside of the house, and then it's the feeder is fed over head to the top of the panel. And here's the interior of the panel. Here are the ungrounded conductors going to the main circuit breaker and the grounded conductor, the neutral, going to the neutral bar. And it's tied to the grounding terminal bar. Here's the main bonding jumper, the screen screw, and this is the grounding electrode conductor going to the grounding electrode. That could be a rod, pipe, or plate. It could be steel pipe. It could be a ground ring. It cannot be the cold water ground solely. If you have cold water, you have to bond it, but you can't use the cold water pipe as the sole means of being the grounding electrode. It has to have a supplemental grounding electrode. And you're not allowed to use metal gas pipe underground as a grounding electrode. Again, it must be bonded to the system, but it cannot be used as a grounding electrode. Grounding systems less than 50 volts. NEC Article 250.20a requires the grounding of systems less than 50 volts in the following situations. So if the secondary is less than 50 volts, this is a misprint. This wasn't supposed to be. They weren't supposed to print this one. They were supposed to say less than 50 volts. But if it is supplied by a transformer with a primary voltage that exceeds 150 volts to ground, then the secondary needs to be grounded. If it is supplied by a transformer that is ungrounded, the secondary needs to be grounded. For overhead conductors outside of the building, it needs to be grounded. So here you go. You have a greater than 150 volts primary and less than 50 volts secondary. The secondary needs to be grounded. If you have an ungrounded primary and less than 50 volts on the secondary, you need to ground. I'm sorry, greater than. Less than 50 volts. See, that's also a misprint. That arrow's going the wrong way. You should say, no, I'm wrong. That's less than 50. This is less than 50. So if you have an ungrounded primary with a secondary that's less than 50 volts ground, it also needs to be grounded. And any overhead conductors outside of the building have to be grounded, even if they're less than 50 volts. Grounding of 50 volts to 1,000 volt systems. If the system can be grounded such that the maximum voltage to ground on the ungrounded conductor does not exceed 150 volts, like 120/240, it has to be grounded. If the system is three-phase, four-wire Y connected and the neutral is used as a circuit conductor, it needs to be grounded. If the system is three-phase, four-wire delta connected and the midpoint of one-phase winding is used as a circuit conductor, it needs to be grounded. So where the system can be grounded so that the maximum voltage to ground on the secondary does not exceed 150 volts, it needs to be grounded. If it's the center of a Y, the midpoint of a Y, and it's used as a phase conductor for the neutral, it needs to be grounded. If it's the center point of one of the phases of a three-phase delta, and it's used as a circuit conductor, then it needs to be grounded. Grounding AC systems over 1,000 volts. NEC Article 250 Part 10 discusses the grounding requirements for systems over 1,000 volts. It also lists additional requirements for derived neutral systems, solidly grounded neutral systems, and impedance grounded neutral systems. AC systems over 1,000 volts must be grounded if they supply mobile or portable equipment as covered in NEC Section 250.188. Other AC systems over 1,000 volts are permitted but not required to be grounded. Circuits that cannot be grounded. Circuits for overhead cranes that operate over combustible fibers in a Class 3 location cannot be grounded. They don't want to lose that that crane operation and drop a load onto those combustible fibers. For healthcare facilities, those isolated power circuits in hazardous locations as provided in NEC section 517.61 and 517.160. So anesthetizing is flammable and your system is ungrounded in situations where they're anesthetizing patients. Circuits for electrolytic cells as provided in section 668.11 and 668.21. Secondary circuits of lighting systems is provided for in section 411.7 and secondary circuits of swimming pool lighting systems as provided for in NEC section 680.23A2. So, cranes that operate over combustible fibers, not grounded. Isolated health care facility in hazardous locations, anesthetizing and wet locations, not grounded. Circuits for electrolytic cells, not grounded. Secondary circuits on lighting systems for swimming pools, not grounded. So here's section 1 review. Suppose loose connection has an exposed bare conductor that contacts the edge of a metal enclosure. Is this an example of a short circuit or ground fault? A single phase system has two legs, leg A and leg B. If leg A is carrying 50 amps, leg B is carrying 45 amps. Current carried on the neutral is how much? And I'll go on to a second video for part 2.